In the previous lecture, I showed that the work done by gravity in its Newtonian form over a closed path is equal to 0. This then means that gravity is a conservative force in its Newtonian form. That shouldn't be any surprise at this point. And then therefore potential energy exists. So now what we have to do here is we have to quantify gravitational potential energy in its Newtonian form. And in order to do so, we have to take a portion of the calculation that I performed in the preceding video. What we have to do is we have to take a look at the work done by gravity from point A to point B in that calculation, but we have to choose point A and B very carefully. Here's then how we set this up. Okay, so once again, what we're doing here is we're quantifying potential energy. Okay, so once again, just for context, let's go ahead and draw the Earth, like so. Right here is the mass of the Earth as a point. And then once again, keep in mind that the center of the Earth is the origin in this description. Okay, and then point A for our object of mass m is just some distance away from the origin. This right here is just generically referred to as r. But then we're going to choose our point B to be infinitely far away from the Earth. So way over here is point B when the distance r is equal to infinity. Okay, and now we set up our work calculation, the work done by gravity, and we use the exact same integral as I used in the preceding video. We do, of course, have to be careful about the limits of integration. Okay, so the work done by gravity is equal to the following integral. Like so. And then we integrate this from position r to position infinity. Okay, the antiderivative that you obtain when you integrate this function is exactly the same as it was in the preceding video, and that's the following. And then what we do is we evaluate the antiderivative between r and infinity. So now plug, first of all, infinity into the expression, and you end up with 0. And then subtract with small r plugged into the expression like so. And then therefore, if you simplify, you basically just end up with the following expression. This expression right here is the equivalent of the following near the surface of the Earth. You lift an object vertically, and then ultimately the work done by gravity when you do is equal to negative mgh. This right here is the work done by gravity in lifting an object from this position to being infinitely far away from the Earth, and it's this quantity right here. Therefore, the minimum amount of energy that you need to use to overcome gravity, the work done against gravity, is the negative of this. So then therefore we write that in the following way. Okay, so the work against gravity is now equal to the negative of the work done by gravity. And then showing all the negative signs, we then end up with the following. The negative signs cancel out, and then we have the following positive value. This is the Newtonian equivalent of the following. You lift an object near the surface of the Earth. The work done by gravity is negative mgh. Therefore, the work that you would do against gravity is positive mgh. And then recall that we interpreted the work done against gravity as being equal to the change in gravitational potential energy. Same thing here, like so. Okay, now change in gravitational potential energy. That's a final value minus an initial value, like so. However, on the diagram above, where should we consider the potential energy to be 0? Should it be, for example, the center of the Earth? Should it be the surface of the Earth? Or should it be infinitely far away? It should be infinitely far away. That is, when r is equal to infinity, this quantity here is equal to 0. That's position B in the calculation above. That's the final gravitational potential energy in this calculation. So the final gravitational potential energy is 0 at infinity. Therefore, you end up with the following expression. Let's go ahead and plug in the 0. Like so. And then just move the negative sign to the other side. Like so. And the initial potential energy on the diagram above at position R is the following negative number. In general, gravitational potential energy, written in its Newtonian form, is the following negative expression. Okay, now in order to begin to wrap your head around the negative sign, first of all, go back to what I said a few minutes ago. The final potential energy in the calculation above is 0 at infinity. That is when r is equal to infinity. This quantity here is equal to 0. Just think of it merely in the following way. How far away from the Earth do you have to be such that the force of gravity exerted upon you due to the Earth is equal to 0? You have to be infinitely far away. Remember that the force of gravity is gmm over r squared. So then therefore, if r is equal to infinity, then the force is equal to 0. So then therefore, if you're infinitely far away from the Earth, the gravitational force exerted upon you is equal to 0, and then therefore the gravitational potential energy is equal to 0. So then therefore the gravitational potential energy has to be 0 at infinity for this reason. Okay, now how can you start to kind of wrap your head around the negative sign? Okay, you can do so in the following way. Let's just take a look at the negative 1 over r relationship. Ignore the numerator, which are all just numbers anyway. Okay, watch how this negative 1 over r term behaves mathematically as we make r on the diagram larger and larger. Now, r on the diagram larger and larger means that you're getting further and further away from the Earth. So then therefore, if you're lifting the object, if you will, higher and higher, what should be happening to its gravitational potential energy? It should be increasing. So now let's see what happens with this relationship here as I make the number r bigger and bigger. Let's just use integer values for simplicity. So let's say negative 1 over 1, negative 1 over 2, negative 1 over 3, negative 1 over 4, and so on. So I'm making the value of r here bigger and bigger as I write these numbers down. So it's like you're lifting the object higher and higher above the surface of the Earth. Take a look at these numbers. As I go in this direction on this simple diagram, are these numbers decreasing or increasing? They're increasing. Negative 1/2 is bigger than negative 1. Negative 1/3 is bigger than negative 1/2. Negative 1/4 is bigger than negative 1/3. What are these numbers increasing towards? They're increasing towards 0. So then therefore, yes, as you lift an object higher and higher, the potential energy increases. But because of the 1 over r distance relationship here in this calculation, we then therefore have to think of potential energy as a negative number for exactly this reason. Once you wrap your head around the negative sign, using potential energy in its Newtonian form is easy to do in simple conservation of energy examples. You just got to be careful of the negative sign. Just don't forget to include that. So then therefore we'll begin taking a look at examples in the next video.